Morning, guys. So, yesterday we introduced to you heat energy. We had one main formula here, which was Q is equal to mc delta T. Q is the heat energy. It told you the relationship between three things depending on how much mass I was trying to heat up, depending on the material itself. Some materials are harder to heat up. The bigger the specific heat, the harder it is to heat up. We saw water was, as a liquid form here, is actually fairly hard to heat up. And as you might imagine, as you heat things up, we expect our thermometer scales to actually go up. Remember, thermometers are some measure of the average energy in the system, and we can just punch through those three terms to actually find the heat that's distributed. One emphasis I want to note to you here, although mass is typically in kilograms here, in many times when we do this chapter, this section here, mass, we actually just use grams, and therefore the heat comes out in joules. Typically, if we use kilograms for mass, we're going to actually end up in kilojoules. But you really need to look out for the units for C. Make sure your units are in such a fashion that all the other units cancel out, so we can end up with this. This formula is great to track changing in temperature. We found that, strangely enough, during a phase change, during the time when this chemical here changes from, say, solid to liquid, liquid to gas, during those condensation, sublimation, those terms there, we saw that the temperature actually plateaued. Because it plateaued, it doesn't let me have a delta T term anymore. What we did is we actually absorbed the C delta T and we put it together in a constant. Only during a phase change, we're going to go Q equals M times L, either LF for fusion, solid to liquid, or LV, that's for liquid to gas. So I just wanted to show you an example of how this would work out here. So let's do a temperature time graph. The experiment for this is always super simple. We're going to take an object. Just for simplicity, I'm going to start it off as a solid. The same would be true if I started off with a gas and I somehow pulled the temperature away. Let's start off again here. Let's start off with 100 grams. That's my block. 100 grams. This one here, let's make it negative 10 degrees Celsius. And right now I'm going to tell you that's ice. The experiment is crank up the hot plate, let the heat that get transferred in there. Experimentally, we're actually going to run into problems where the heat may be delivered to sort of the bottom parts of the ice more than the top, so the melting might be uneven. So maybe I could do this more so in a microwave where the heat is more uniformly distributed here. But in some sense here, we're going to try to melt this here. And what we're going to do is we're going to look at the clock and we're going to see what does my thermometer read as the heat is being applied to this object. So I'm going to draw for you the temperature time graph first and then get you to do a few calculations. Right now I have the block of ice at negative 10 degrees. As ice, the particles are just vibrating in place. Again, we haven't hit the special temperature of 0 where it's hot enough to actually break apart the structure. Like we saw towards the end of yesterday's lesson here, this one here steadily climbs. At 0 degrees, something surprising happens here as the temperature ends up plateauing. If we actually did this experimentally, you might find that this plateau may not be perfectly straight across. We're going to imagine an ideal world. Sometimes the plateau here might take a little bit of a leg. It might actually stretch over a little bit. In fact, chemists will use this here. We expect the melting point to be one uniform temperature change. If there is some difference in temperature for the melting point, this is actually a measure of purity. It's a measure of how evenly the heat was transferred in. They can actually use this to figure out, to test how pure their products are. But again, we're going to keep it very simple here. Keep it with delta T equals 0. As you heat up this ice here, we're going to go from having 100% solid to 100% liquid. That's just going from solid to liquid melting. So we're basically applying all that heat. We saw with numbers last day, it's a ridiculous amount of heat that's needed to do this. Eventually, when it's all liquefied, the particles can now start speeding around a little bit faster. As the average energy goes up, the temperature goes up. Note that the slope is a constant slope. But we're going to see with our specific heats, the slopes here as solid is different from liquid. So you do need to be really careful what state of matter it is. At 100, we get the other special temperature for water, plateaus again, and then it levels off. What I want to do is I want to take this 100 grams and I want to make it up to 110 degrees worth of steam. And if you remember, steam is just gaseous water. In this case here, so that's the setup. I need to give you a bunch of these specific heat capacities here. I'll give you the specific heat of ice. You can just look up these numbers. 2.06 joule per gram Kelvin. The specific heat of water. Water implies H2O as a liquid, so this was the 4.18 we used from earlier. The specific heat of steam. So specific heat when it's actually hit the gaseous state here. This one's dropped back down to 2.02. Every chemical will have different constants for their different states. And because we do have phase changes, I'm going to give you the latent heat of fusion, the melting We used this last day, kilojoules per kilogram, and then we're going to use latent heat of vaporization. This one even more ridiculous here. First thing is ridiculous because you'll notice this is talking already in the kilograms, and this is some hundreds of kilojoules, whereas earlier it was just grams and only like single digit of joules. So ridiculously high. This one is actually some 2,000 in those same units, kilojoules per kilogram. Again, we're going to have a problem because some of them are in joules, some of them are in kilojoules. Probably for simplicity here, we can convert, let's say, everything into kilojoules, and therefore it's easier to take a look at. In this case here, we actually need to break the heat term. Heat is a scalar. We just heat up all the little bits of it. We're going to need to heat up the Q for ice from -10 to 0 degrees. That's just for this first leg. Then we're going to do the Q for the melting. That's going to be the second leg, the plateau. Then I'm going to do Q for water. I'm just taking all the little bits here, I'm breaking it down. So going from 0 to 100 will be this third leg here. I'm going to add Q for the boiling. That's the other plateau. That's the one that's going to use vaporization, huge number. And they heat it up to 110. So heat for steam and going up from 100 to 110. So 5 different parts. Again, thankfully energy is a scalar, so there's no breaking down of components. You just add up all the little bits. Whenever there is a temperature change, so whenever there is a sort of a slope on this graph here, you can use MC delta T. So MC delta T here, MC delta T, MC delta T. Whenever there's a phase change, we can't use that. We have to use ML plus ML. Be careful depending on what state I am, ice, water, or steam. I want to make sure I use the correct specific heat. So without further ado, let's take a look here. We took what I said was 100 grams. Let's go 100 grams. I'm just going to show you the units for this one. 100 grams, the constant for it as a solid is 2.06 joule per gram Kelvin. I want to heat this up here from -10 to 0. We're going to see it's, delta T is final minus initial. So you could write 0 minus a -10, or just in your head you can go, oh, that's just 10 steps, so that's 10 there. I'm just going to punch in that first term, just show you what I'm going to do. 100 divided by 2.06 times it by 10. This is going to give you 2060 joules. Unfortunately here, because I'm going to end up with kilojoules out of here, yes, I do end up wanting to add the energies, but I can't add a joule with a kilojoule. So what I'm going to do is, for these ones that are coming out in joules, I'm actually going to divide it by 1,000. By dividing by 1,000, that converts me over. This is now 2.06 kilojoules. Now that they're all kilojoules, I can add up all the bits. So with that in mind here, I can then add up the next one. So for the melting, I'm going to take the same 100 grams, but I need to convert to kilograms. So 0.100 kilograms. Again, I'll show it to you with units for this first one. Latent heat was 334. This was specific here for liquid water. So that's going to be kilogram, cancels kilogram. That already comes out in kilojoules, so that's perfect. 0.1 times 334 is 33.4. So this one here adds. And now that they're both in kilograms, kilojoules, I can add these two easily. You cannot add a joule to a kilojoule. But you basically just go add. Let's do the same for the other three terms here. Once it's become water, I'm assuming we're still 100 grams. For liquid water, we're actually 4.18. So 4.18. As a liquid, it's actually harder to heat up than as a solid. You can again go T final minus T initial. So 100 degrees minus 0 means 100 steps. I need to divide it by 1,000 this time just to convert to kilojoules. I'm going to take that same mass. I'm assuming that there's no loss. Again, this is a perfect world here. 0.1. Latent heat is a ridiculous 2260 for boiling. And then one last term here. You could have done this in separate steps here, but I just want to show you the big picture. Plus, same 100 grams. The constant has dropped back down to 2.02. Times it by another 10 degrees, divided by 1,000 just to convert the units. So let me just add up the rest of these bits here. 100 times 4.18 times 100 divided by 1,000. This gives me 41.8. Remember, I'm dividing by 1,000 just to get it to kilojoules. This one here is 226. Last one, 100 times 2.02 times 10 divided by 1,000. This one here is giving you 2.02. So now that they're all in the same unit, not only can I put them all together and I can find the total heat transfer, 2.06, add 33.4, add 41.8, add 226, add 2.02, and this gives me here, I need some 305.28, I'm just going to round it to 236 fakes, 305 kilojoules for all this to happen. And I wanted to show you, you can't just go MC delta T just straight from ice to steam. The reason for that here is because of the different states, the specific heat is actually different. So just because I'm water as a chemical, it doesn't mean as solid, liquid, or gas, I'm the same numbers. And also, I need to deal with these regions. Even though the temperature looked like it's plateaued, it's flattened, there is a ridiculous amount of heat that's actually needed to do that. You can actually see that again a little bit here. Just looking at the numbers, these are all kilojoules. Notice that in melting and boiling, it's in the tens and the hundreds. This water term was fairly big because this was actually 100 steps. But if you compare just 10 steps here, that's only 2. This is only 2. Nowhere near as big as these tens terms and in the hundreds. So that's how you do with this temperature time sort of setup here. Again, I want to remind you energy is a scalar, so that's why I didn't need to worry about components or breaking up x and y. I can just add up, okay, do this heat, hit this heat, this heat, this heat, and you can just add them all together. To finish off this section on heat energy and the energy chapter, we're going to go through a little bit of theory. We're going to have a look at just thermodynamics in general. I used to have a TA that liked pronouncing it thermodynamics, right? So we see dynamics here is sort of the analysis of, right? So dynamics in our forces chapter, we're looking at pushes and pulls. In this case here, we're looking at the mechanics or the workings of the thermochemistry. We're interested in how heat gets transferred, why things go hot to cold and not cold to hot. It's basically since our universe was formed, there were a few laws that were set in place. So again, just a little bit of theory just before we get to our last question. We have something called the first law of thermodynamics. The first law of thermodynamics here is basically a statement of energy conservation. So we've said this before, while energy cannot be created or destroyed, they just word it a little bit differently for the first law. For the first law, it says the internal energy, that is the energy that's inside the system, the internal energy only changes if work is done or heat is transferred. Those are the only two ways that the internal energy actually might change. So they actually write that out in a formula here. If you want the internal energy to change, again, strangely enough, they use U for it, so delta U. If you want the internal energy to change, the only thing you can do is you can do some work, you can do W, or you can do a heat transfer, what we've been saying is Q. So the picture that they're implying here is, imagine we have our big universe again. So universe is way too big a place to study. We're always going to be looking at maybe two cars colliding, so that's going to be our system. This is the part that's under study. What it's saying here is energy conservation, we've already said, applies to the entire universe. Whatever energy since the Big Bang, it doesn't matter how fast the universe is expanding, how far spread out it is, that's actually part of the problem here. But whatever total energy that's stuck in this box here, you can make a note here, energy cannot be created or destroyed. That's what we said earlier, right? When we compared it to momentum's conservation as well. So energy can't be created or destroyed. Whatever number you have inside the box, that's your total number. You have to stay put with that. Because we are going to arbitrarily define our system. So this time it's a car collision, this time it's a bomb exploding, this time here it's a pendulum problem, roller coaster style problem. Because it's totally up to us how we define system, the internal energy, so the U inside the system, should be the same. That number here should be constant. But because the system is an arbitrary decision on our part, what we can do is we can actually apply some work to it. I can actually, let's say this is a block that's just sitting at the bottom of the ramp. I can actually supply a force over a distance. I'm actually putting in work, and therefore my internal energy would go up. It seemingly be increasing energy. Oh no, the number goes up. Doesn't mean it's not conserved. Well, if the number of the system goes up, that means the surroundings had to have lost the same amount of energy. Or vice versa here, maybe my system is a car, it's burning the fuel. It actually allows, by burning the fuel, converts the energy, and it allows me to do a job. So it might be a minus work. It might actually apply work to the outside. Again, I think of like the money analogy here. You can put, let's say, $5 in. System goes up by 5, surroundings goes down by 5. Or the system might lose 10 joules of energy, goes down by $10, and then it's because the surrounding goes up by $10. Overall, you notice that the universe total energy still stays the same. So work is one way you can change the energy of my arbitrarily defined system. The other way here is you can apply some heat. So like we've done in these questions here, let's stick it into a microwave here. Let's add some heat. Oh no, it looks like my system has actually gone up in energy. Again, whatever the system goes up by, the surrounding, as long as it loses the same amount, energy is still conserved. Or maybe the heat is lost from the system here, minus Q. So that's why it's saying the internal energy should not change as long as there's no work or there's no Q. And I just want to remind you again, energy is scalar. Energy should be positive. What we're using positive and negative for in this chapter is just to imply, is it into the system or out of the system? It's positive if we're talking about into system, work that's being applied, you transfer heat going inside. If it's negative, it doesn't mean backwards anymore. This just means out of system. So it's just implying an energy gain or an energy loss in chemistry, endothermic or exothermic. So this one here, you can just summarize all that here. We're actually playing a very depressing game. This one here is actually says you can't win. You can't create a device that ends up generating more energy than you had before. So in the past, they tried to do what's called a Rube Goldberg machine. They tried to design a machine that you put in less energy, and somehow out of that actually comes more energy. What this first law of thermodynamics says for you here is, no, the total amount of energy is going to be fixed. Sure, you might be able to transfer from place to place, but you can't actually suddenly have more energy in my universe. That one there is fixed. So that's already depressing. Then comes the second law here. We get an even more depressing picture. So this one here is the second law of thermodynamics. This one here is actually worded in many different ways. This one actually explains why our hot cup of coffee gets cold. We're going to use the terminology here. Systems tend towards, or nature tends towards greater or maximum entropy. We're going to study entropy in a little more detail in our chemistry courses. Suffice to say for us in Physics 11 here, we're going to say entropy is a measure of the disorder. Sometimes they use terms like randomness. Sometimes they use terms like chaos, which is chaos. So the amount of chaos in the system here. This one here, again, the applications. The applications are, why does hot become cold? So that's how the second law is being applied. Let me just give you a quick feel of what's happening here. So just a quick mechanical analog here. Let's imagine I'm standing at the top of the hill. Let's imagine I have 3 basketballs. And let's say the basketballs, I painted half of them and I've arranged them really neatly. In this case here, currently the basketballs are in what's called a very ordered state because they're all neat. They all have their painted side down. Because entropy, we're going to use capital S for it, because entropy is defined as disorder, it's non-order. What's happening here is, this one here is ordered. That means I have very low entropy. I have low chaos because it's very orderly. My experiment here is very simple. I'm just going to roll these balls here down the hill. What are the chances that the balls, by the time they just randomly bumped and whatever, what are the chances that all the balls here may have completely flipped? Hopefully you were able to say it's probably not very likely. The chances of all this to happen so perfectly, probably not likely. It's not likely to be the same order as before. Probably you might get one rolling this way, one rolling this way, one rolling this way, or some other configurations. You can take your pick here. There's many different ways. There's many other varieties. And if you just look kind of big scale here, all of these ones here are sort of chaotic. In fact, what's happening here, if you want to get into the language, each of these is called a microstate. Each of these is a possibility that these balls here could have landed in. In fact, for me to get exactly this one, or this one, or this one, it's equally unlikely. The chances of this one exactly being this orientation and this way, it's equally unlikely. But I wouldn't even take a second look. I would just group these together and I'd say, well, the chances of me finding it in one of these states here is just chaotic. One of these random states here, each state, probability-wise here, might be equally unlikely, but there's a whole lot more microstates, a lot more ways that I would just define it. Oh, that's just chaotic, that I would be expecting. So in this case here, the second law here, we said nature, the universe is always tending towards greater entropy. Things are naturally getting to be a more chaotic state here. The more chaotic state here is higher entropy. This happens with your rooms. I'm sure none of you, if just sort of saying, just going back to your room, you'll be like, I'm going to make my room messy today. Okay, the room just naturally happens that way, right? It may be neat on Sunday, and then over time, you throw your shirt over here, you throw your pants over here, your books are all over the floor and whatnot. Things just naturally get more and more messy. So more of the story there is, if your parents say, clean your room, you can just say, I'm following the second law of thermodynamics, okay? Things just naturally get more chaotic, right? Now, what you can do is you can, I can expend some energy, expend some time here. You can walk to the bottom of the hill. You can start putting the balls here back in place. We're playing a very depressing game here that the second law says the entropy in the universe, sure, you might be able to put your room in order, put the balls back into a nicely ordered state, but it turns out in the amount of time and energy that you're trying to order your system, somewhere else in the universe, the system has gone crazy. The system has already got way more chaotic and way more random than you. So this is sort of continuing that disorder, that sort of depressing picture here. We already said you couldn't win. You can't create energy out of nothing. And in fact here, this statement here says you always lose. Every time you transfer energy, yes, the total amount of energy, the total quantity is conserved, but because we're going to lose energy here, overall the system is going to gradually drop in energy. And in fact, this is what's happening as our universe is actually stretching out and expanding. All that heat that was in the Big Bang, it was a really hot, murky substance there. As it actually expands, we've been cooling. Now our empty space is about 3 or 4 Kelvin. We're only a couple of degrees above absolute zero. It's because the heat is dissipated, and basically it's never coming back. You always lose, or you can say here, you can't break even. And again, I want to be really clear here. We're not saying that energy is suddenly lost, okay? The quantity, the amount of energy stays the same. Quantity stays the same because we said E in equals E out. But what's happening here is the quality is degraded. So because of heat that's dissipating, it just kind of leaves into the environment. You can't collect it back up again. You may have put 100 joules in, expecting to get at least 100 joules out because I can't break even. I can't get more. I can't get 120. But usually what we get is only maybe 80 joules out, which is why we have the whole notion of efficiency. We're not in a perfect world, so we don't end up even getting the same amount back from our work. So we can actually utilize some of these concepts here. That was just a little bit of background to just finish off this last sort of conservation style problem. We're looking at conservation in terms of heat. We know this in the background. We know we can't win. We know we always lose. But just for simplicity, because we're in an ideal world, we're going to make some assumptions for these questions here. Let's assume we actually are 100% efficient. That's best case scenario. That's when we have no heat loss to the environment, 100% efficiency, and what we want is an isolated system. Turns out for systems, you can actually arrange them as either a closed system. In chemistry, a closed system would basically be you have a cap on top of it. Basically, if you have gases, they can't escape. It could be an open system. An open system, as the name suggests, your beaker is sort of open to the environment. Not all reactions generate gases, but if I did have gas, that one there would be open. The problem with both closed and open systems is the outside here is probably made out of some glass. It's sort of conductive in terms of heat. You might have heat that sort of gets lost or heat that gets input into the system. It doesn't really store heat very well. That would go against you being 100% efficient because heat is being lost. What we want is we want to make the system heavy duty enough for my beaker, maybe like a double-walled thermos or whatever. It's better. You definitely want to cap the top. And basically, I want all the heat transfer, all the heat to stay stuck inside. Not just the matter and the particles to stay stuck inside. I want to make this heavy duty enough that basically no heat escapes. A thermos is a good approximation. If you put hot water in the morning, it'll probably stay hot for some 7 hours, 8 hours or so. Compare that to, let's say, an open mug or even just a closed water bottle. But eventually your thermos also cools down and isolated as a sort of a perfect thermos. Basically, whatever temperature you have, yeah, you might get still transfers between liquid and the gas and inside the system, inside the container, but we're going to assume that it's isolated. So we're going to say all that to say no heat loss. No heat loss to the surroundings. Again, this is perfect world here. No heat loss to the surroundings. So in that situation here, we can end off with our last question. Let's imagine here's our setup. I'm going to start off with a block here. This block here is going to currently be, let me find some numbers here. Let's make this block here 50 grams. This is going to be aluminum, and aluminum is a solid. The constant I had given you yesterday is 0.90 joule per gram Kelvin. That says it takes 0.9 joules to heat up 1 gram of this material by 1 step on your thermometer scale. And currently here, let's say this is I've artificially heated this up, and I've heated this up to 80 degrees. Alright, so I somehow put on a frying pan or something, and I heated up this block here. In the chemistry context, maybe it's a chemical reaction that heated it up, but in this case here it's more simple. We just say, okay, this block here happens to be hot. What we're going to do to cool this down is we're going to drop this hot object into some water. Let's say this is my mug of water again, 250 milliliters, which I know for water is grams. Again, mils is grams only for water. So there's water there. Let's assume my water, I just got it from the tap. Let's say it's 10 degrees, and the constant here is similarly 4.18 joule per gram Kelvin. Water as that chemical, it's a little bit harder to heat up. We had seen the moderating effect in yesterday's lesson. So that's the system. We're under these assumptions here, assuming the walls are made out of something heavy duty that doesn't allow for any heat transfer, any loss to the environment. But what's going to happen here is when my hot block over here encounters a relatively cold environment, that's perfectly set up that heat gets transferred from hot to cold. Again, that's something that comes out of the first and second laws of thermodynamics. It always goes hot to cold. Your cup of coffee doesn't naturally suddenly get hot, even though I would like that. We make this an isolated system, so although there is going to be heat transfer between the aluminum and the water, we're assuming that there's no heat loss to the environment, which is the main problem in some of these experiments. So based on these assumptions here, because we're dealing with some M, C's, T terms here, what we want to say here is we want to say, well, the aluminum that's hot is going to end up losing energy. The heat that the aluminum loses, and comparing it to the heat that the water gains, right? I know the water is relatively cold. Water is going to soak up some of the energy change. Because I am under this assumption here, 100% efficient, assuming that we're isolated and there's no heat loss in the environment, I can set these two as equal. So this is in a perfect world. This is just for calculation's sake, just to make the math easy. Because I do have a Q term on both sides, what I want to do is I want to go a MC delta T. And on the other side here, I want to use a MC delta T. I'm just going to remind you here, on the left-hand side in red, it's actually going to be all the aluminum numbers. And on the right side here, it's going to be all the water numbers. So just because it is MC and delta T doesn't necessarily mean that the same numbers going into it. So let's just plug and play here. I'm going to purposely leave a mistake if we can here. So let's go here. This one here is 50 degrees. So we have 50 degrees. I'll even show it to you with the units just so that you can see the units canceling out. So we have grams. This one's going to be 0.90 joule per gram Kelvin. The delta T is going to be hard. The delta T for the block needs to be from 80 degrees down to whatever final temperature that I cool off to. The water actually goes the opposite, goes from 0 degrees up to the final temperature. We call that final temperature here the equilibrium temperature. Basically, heat is going to transfer as long as there is something that's hot or cold. We want to find what is the equilibrium temperature. By the time both of them are at the same temperature and there's no more heat transfer, how hot is it? Intuitively, we'd say it should be somewhere between 10 and 80. The hot block of aluminum has cooled down, and the water was already cool at 10. It should be increasing some amount. So we're going to use that here. For change in T, I'm going to go TF minus TI. I don't know the equilibrium temperature, but I know the block started off at 80. Again, I showed it to you with all the units here. Usually, if mass is in grams, specific heat will cancel out in grams. We'll end up with joules, just like I showed you earlier. We'll do the same for the water side. We have more water, so 250 grams. The constant for water is a little bit bigger, so this one here is going to be 4.18 joule per gram Kelvin. As you get more practice with this, you don't need to put the units inside here. And then just to show you the temperature change here, whenever you have delta, it's always TF minus TI. So we're going to take that same equilibrium temperature, that's what we're interested in, TF minus the true temperature of my initial temperature of 10. So that's how I'm setting up here. Again, I'm purposely leaving a mistake. You can still copy along here. I'll show you when to stop copying. So 50 times 0.9 here gives me 45, our units have already canceled out here. So we have 45 times TF minus 80. This has to equal to, I just did 250 times 4.18. This is equal to 1045. 1045, again we have TF minus 10. You can ask yourself what the next math step would be. Although you could collect up the 45 and the 1045, we still have to deal with this problem that the TF is stuck in a binomial. It's stuck in this bracket. So what we can do here is we can actually distribute. Again, you can keep copying this part, even though I purposely left a mistake. 45 TF minus 45 times 80. This one gives you 3600. I'm going to distribute, multiply that 1045, the opposite of factoring. I'm going to multiply all that in. And then now I have it out of the binomial, I can just collect the like terms. So again, I purposely been leaving the mistake. Don't copy this last little bit just yet. We'll correct it afterwards. I'm going to bring the 45 over. So minus 45. Don't copy this in the black just yet. So 1000 TF. I'm going to add the 1045 over. 10450 plus minus 3600. I should be getting 6850. And there we go. Our final temperature is 6.85 degrees. Huh? What's wrong with this? Right. We had said the block was going from 80. I'd expect this one here to cool down. But the water was already 10 degrees. I would have expected the hot object, because water soaks out the temperature, I'd expect it to be something hotter than 10 degrees. And yet, seemingly as mathematically, we have, wait, how could our temperature finally be 6.8? Something is wrong with this picture. Nothing's wrong with our math, right? I just distributed everything correctly. But something is fundamentally wrong. Let's see if you can spot it. You can pause it and you can see if you can guess for yourself. It's actually, the hint here is actually back to the beginning. Yes, we were under this ideal assumption. Yes, we've been trying to put these sides here equal so I can do algebra on them, right? There's no sort of friction loss or anything like that. But it's actually a little bit sneaky in here. The problem actually comes from this statement here. The Q that the aluminum loses is matched up to the Q that the water gains. Because there is this whole notion here, well, aluminum is going to drop by heat. Maybe aluminum drops by $5. Maybe it's minus 5. Water is supposed to pick up 5. It's supposed to be plus 5. Right? We had said that with energy conservation, what one side drops, the other side has to pick up to make sure energy is conserved. We can't win. But what we're trying to say here is, yeah, this side here is minus 5, this side is plus 5, but no, minus 5 is not equal to plus 5, right? They're actually negatives of each other. So what we're actually missing, and I purposely left this mistake in, to make sure this is equal, because one side is negative and one side is positive, imagine before setting them equal, imagine putting a minus to one of the sides. Some people like putting the minus on the loss side. Doesn't really matter. I can multiply both sides by -1. It can jump over. But basically what that does is it recognizes the direction, because one is a loss and one's a gain. If I take a negative of one of the sides, now I get positive 5. Yep, that matches up with positive 5. I'm still saying loss equals gain, but I do need to propagate this negative through. So I purposely left in that problem there. There should be a negative. There should be a negative here. There should be a negative. Negative. I need to up this to a positive. When I tell you to stop copying, I don't want this, right? Now with that negative in there, distributed correctly, I can then do my algebra. Let's add the 45 over. You can copy this last part. 1090 TF. I'm going to add the 1045 again. 10450 plus 3600. This gives you 14050, and it leaves you with a TF of 12.9 degrees, give or take 13 degrees or so, right? 2 or 3 degrees. And at least we breathe a sigh of relief here. We are getting something between 10 and 80, which is what we expected. Are you surprised that the hot block of aluminum actually dropped 80 to 12 is almost 50, 60 degrees or so, whereas water was already 10 degrees, water only heated up by 2, 3 degrees or so. Why was there this such a dramatic difference between how much the aluminum cooled down and the water heated up? Based on the math here, you should be able to see here, it's because water has a bigger mass. There's a lot more particles of water. I need to heat up each of those particles. Aluminum is way tinier in terms of mass. But the other more important reason here is water is a chemical which actually has a higher specific heat. It takes more energy to heat up the water than it takes for the block here to actually lose steps on the temperature scale. So that finishes off here. Gave you a little bit of background on thermodynamics, first law, second law here, and then we can apply that to this sort of conservation style question. We'll do a summary of the chapter in the next lesson. We'll take another closer look at simple machines, and that'll be it for our chapter. If you have any questions, just let me know. Thanks, guys. Take care.